This video is about the bandpass filtering script that is provided in figure 20.7 of the Applied Analog Electronics textbook. The course is not about programming, so I don't expect people to be able to create their own bandpass filtering scripts, but I do expect people to be able to read the one that's provided and understand how to make minor modifications to it. So let's take a look at it. Okay, the first part of it here, the very first line, is just saying, hey, this thing should be run with Python if you see this thing as an executable script. The way that I used it in the previous video, where I explicitly invoked Python and then gave the script name as an argument to Python, means that this first line isn't really necessary. However, if you've made this an executable and invoke it directly, this will cause it to call Python. The next line, the from future stuff, is just to make the program, if it's run under Python 2, behave more like Python 3. That's what the from future stuff does, to change the print function and the way division is done so that they behave like they do in Python 3. Import sys, import numpy as np, import, and from scipy import signal. All three of those are grabbing stuff from packages that are needed in order to run the script. The sys package is needed in order to be able to run reading from standard in and putting output to standard out. The numpy and scipy are numerical and scientific Python packages, and the signal processing that is being done here, the filtering, uses the signal package from scipy. You need to have numpy and scipy installed with your Python. If you use the Anaconda installation, which is the one I usually recommend, that automatically includes numpy and scipy, and you don't have to do anything special. Okay, this next try statement here is kind of complicated, and if you're using Python 3, it's totally unnecessary. What it is an attempt to get zip to behave the way it does in Python 3, even if you're running an early version of Python, and it will work even with quite early versions of Python. Now, if you're doing the Anaconda install, you're probably installing Python 3, and so all this try stuff basically ends up just saying, oh, that didn't work, that didn't work, that didn't work, oh, it must be in Python 3, don't do anything. So if you're always going to be working in Python 3, you could strip out this try block here, and you could strip out the from future import, because all those are intended just to make Python 2 behave more like Python 3. Okay, so now let's get into the real guts of the program. The first thing here is sampling frequency is set to being 20 Hertz. This is the default sampling frequency that it assumes you are using. However, it's going to make an attempt to change the sampling frequency later on if it notices that the sampling frequency is different. Okay, the times equals square brackets and the values equal square brackets. These create two lists or arrays, however you want to think of them, which are going to be the data read from the first and second columns of the input file. The first column will be a time, the second input will be a voltage or other value, the thing that we're going to filter. Okay, and then we've got a chunk here that is reading each line in the standard input, and if it begins with a pound sign, then it's a comment. But we're looking for a particular type of comment, and that is if we have a comment that starts with pound sign recording every, exactly the way it's written here, then it's going to extract that line and it's going to look for 20 Hertz in parentheses, or whatever the frequency is in parentheses, because this is the way that Teradek reports the sampling frequency. And so if it sees this comment line, it's going to assume that it's looking at a Teradek output file and will grab the sampling frequency from that. And that's what this float fields 1 split 0 does, is it finds that 20 that's after the parenthesis and says turn that into a floating point number and make that the sampling frequency. All the other comments, it just ignores. Okay, well, it doesn't completely ignore them. We'll get to that in a moment. Because if you notice up above, I did a print line.r strip. And that printing is echoing all the comments to the output file. So every comment that's in the input file gets echoed to the output file. Okay, so if it's not a comment, if it's thinks it's a number, it's going to split it into fields. And I've used a rather old-fashioned way of doing this here. I probably would write it differently if I was doing it now. But what it has done is it's converted them to floating point numbers. So the fields here are each of the columns of that input file converted into floating point numbers. And if there's at least two of them, it'll put the first one into the times array, onto the end of the times array, and the second one onto the end of the values array. And then when we're done with this whole thing, we're going to turn the values array into a numpy array, because the filtering software assumes that you've got numpy arrays and not just ordinary arrays. It's a slight flaw in the way the signal processing package is written. It should do the casting itself, but it didn't, so I did it for it. Okay, so now what we've got is we've got an array of times and a numpy array of values. The next chunk of code here, we're going to define the corner frequencies for our filter. So here I've defined one to be 0.3 hertz and one to be 6 hertz, the low end cutoff and the high end cutoff for a bandpass filter. Unfortunately, the signal processing package doesn't take hertz as its specification for what the cutoffs are. It knows that it's got a sampled thing, but it doesn't know what the sampling frequency is. And so you have to scale these things to being fractions of the Nyquist frequency. That's what it wants as inputs. What fraction of the input frequency of the Nyquist frequency is your low pass, or is your low corner frequency? What fraction of the Nyquist frequency is your high corner? And so take the low end cutoff and divide by half the sampling frequency, which is the Nyquist frequency. Take the high end cutoff and divide it by half the sampling frequency. And notice I did this in 2 steps, so there's a very explicit place where I have this is the cutoff frequency in hertz. So it's very easy to modify this. If you later on have to change the script, say you don't want 0.3 hertz to 6 hertz, but you say you want 0.5 hertz to 50 hertz, it's just a matter of changing these 2 numbers. Okay, the bandpass filter is going to pass frequencies between the low end cutoff and the high end cutoff. And it's going to attenuate everything outside that. And what the SOS band here is getting from this signal.iir filter is it is getting a description of the filter, what parameters you need in order to do the computation. And it's going to have a number of things here. We're specifying that it's going to be a 4th order filter. That means that the drop off on those sides of the filter is 4 decades per decade, which is good enough for just about everything we're doing. You can tweak this a little bit. If you set it to be very high, you might end up with numerical instability and the computation may not work. Probably can go up to 5th or 6th order here without too much trouble, but 4 is a reasonable number for us. Okay, the WN, that's the window, is going to be those 2 parameters that we computed above, the low corner and the high corner as fractions of the Nyquist frequency. Then we're going to say that the filter type, B type here, is a bandpass filter. There's some other different options. You can look up the documentation for the SciPy signal package to find out what IR filters options are besides bandpass. That's the only one you really need for this course, though some students have used band stop filters also. The type of filter here, I'm using a Bessel filter. Bessel filters are good when you're interested in what's happening in the time domain, because they provide the sort of the least distortion in the time domain. What's called the group delay is basically constant. You get about the same amount of delay for all frequencies, rather than some frequencies getting delayed more than others. It's not exact, but it's sort of the best compromise, and this is what Bessel filters are optimized for. You can use other filter types here. It won't make a huge difference in anything we do. The output type here, SOS, is the format of what sort of what form the parameters are going to be in. This particular form is the one that you use with the SOS packages. These are numerically much more stable than some of the other options, and so basically this is the only one you should use if you're at all worried about the computation working correctly. All right, so we've got, then we're going to do the filtering itself. And what that does is we have the SOS band, the set of parameters that we defined the filter with, and we're going to take the values and pass them through this SOS filt. Now the reason the word filt is in there twice is that this particular thing actually filters the signal twice. It takes the signal and filters it once with the time running forward, then it takes the output of that and filters it again with the time running backwards. Kind of a weird thing to do, but it has one really nice property, and that is that any delays that the filters put in when you're going forward get reversed when you do it going backwards, so things end up at the same time, sort of in the same place in the array as they were initially. And that's a very nice extra property to have when you've got something you don't need to do real-time filtering on. If you've got something where you've got the data, all the data before you start, you can do this sort of non-causal filtering. It's something that you need to know what's happening in the future in order to run time backwards. But if you've got a recording, you can take this recording and do this sort of filtering with it. And like I said, that leaves everything sort of undistorted in terms of the delays. And that's one of the reasons why the choice of Bessel filter here didn't really matter, is because even if we'd had a filter that introduced different delays for different frequencies, the filt would undo that, fix that for us. Okay, so that was the bandpass filter. The bandpass array now has the same times as the original values, but filtered values now rather than the original ones. We also have a low-pass filter here, and this low-pass filter, I'm using the same corner as I used for the bandpass filters. So this was the low end of the bandpass filter. That's now going to be the high end for this low-pass filter. So I'm going to take everything below that frequency, doing a low-pass rather than a bandpass filter. Again, I used Bessel, output SOS, and I do exactly the same thing. The low-pass array now is going to get this filt version using this set of parameters on the same set of values we started with. And then I'm going to print out a couple comments that describe what I did. The first comment that I'm going to print out is that there's Bessel bandpass, and I'm going to give the two corner frequencies here. And then I'm going to say there's a Bessel low pass, that give the corner frequency for that. And those are just printed out as comments to the standard output file. So at this point we printed out all the comments that were in the original file, printed out these two new comments. Now we want to print out 4 columns of output. I want to print out the timestamp, the original value, the bandpass value, and the low-pass value. And that's what this for loop and print do. The for loop says, okay, zip together the 4 arrays, so that instead of having 4 separate arrays all the same length, I'm now going to have effectively one, it's not really an array, it's an iterator, but I'm going to have one list of things, each of which has 4 elements in it. The next element from times, the next element from values, the next element from bandpass, and the next element from low pass. And what this is going to do is it's going to say, take those 4 values and call them TV, B, and L, just so they have names. And then I'm going to print out in 0.7f, 0.6f, 0.6f, 0.6f. These are the formats I'm going to do, number of decimal points after the number of digits after the decimal point, I should say. And then I'm going to print out the T, V, B, and L. And there's going to be a tab between each of them, so I'm getting tab-separated values here, which is the format that the Teradata files are in. So T, V, B, and L are going to be columns 1, 2, 3, and 4. And that's it. When I'm done with that, it's the end of the program. So if you need to modify the program, generally the things you'll need to do is you might need to change your corner frequencies. You might need to do something other than a low pass for your fourth column. You might want to extract not the first and second column, fields 0 and 1, but you might want to do the first and third column. So if your data in your input is not in your second column but is in your third column, you can change which field you're inputting here. Though you might want to make sure that there are enough fields to do that with, because this one is only checking for there being at least 2, because it's only looking at columns 1 and 2. If you want to grab columns 1 and 3, you want to make sure there's at least 3 fields, and then you would grab fields 0 and 2. So you could change which columns you read for input. Change the corner frequencies. You could change whether you're doing bandpass or low pass, or you could even do something where you take the bandpass signal and do some other filtering on it afterwards. Like you could take a bandpass and then do a band stop on that. And basically it's the same sort of thing. You create a filter, and then whatever you're trying to pass through the filter goes into the second argument here, and you stick it into a new array when you're done. Okay, so I think that's enough sort of explanation of what this filter script does. You probably won't have to do much modification of it for the blood pressure one, which is what it was originally written for. You may want to use it later on for the pulse monitor lab, though you might want a slightly wider bandwidth for that. And even later on, the end of the course, we do an EKG lab, and for that you definitely want a bigger bandpass range than the one that we use here. But those modifications, as I said, are very easy to make.